Aloha and welcome to our video on the properties of stars. In this video, we'll describe what astronomers can learn by studying star properties. We'll explain how distance affects parallax. We'll list the factors that determine a star's apparent magnitude. And finally, we'll describe the relationship shown on a Hertzsprung-Russell diagram. Okay, so if we take a look at this picture here, what we're looking at is a picture of the constellation of Orion. Now what they did is they took the stars, the brightest stars in the sky, and they grouped them together and formed a picture, and they called those pictures constellations. And most of them are going to have a story associated with them so that we could share that story. So this is what people would talk about before TV and radio and things of that nature. Now Orion's kind of an interesting constellation. It has the belt that everybody's familiar with, the three stars here. Alnitak, Alnilam, and Mintaka make up those three. We also have a couple other stars of note. We have Betelgeuse over here, and then we have Rigel, which are the two brighter stars in the constellation. We also have Saiph, which makes up the other knee, and then Bellatrix. So you can see that we have our stars. The bigger ones will have names. Other ones will be named after the constellation they're in. Now, constellations in modern time aren't necessarily these pictures, although we still know them, but instead they represent like what you would see in that red line, and that is an area of the sky. Now when you look out into space and you see the stars, we're going to see a bunch of different things. This is what we tend to think that it's going to be like, a bunch of individual points of light here. But we'll notice that we also have these clouds, and these are nebulas, and these are where our stars are actually formed. So we can see those out there, these clouds out, when we have a better telescope or a better picture that we can take from, like, say, the Hubble Space Telescope. But this gives us an idea of what it is that we're actually out there and looking at in our night sky. Now, how big is a star? That's one of the interesting things that we have to figure out. What we noticed is there are these binary star systems. Okay, so binary means two and then star system. So we had two stars that were out there. And by looking at how these two stars interacted with each other, we were starting to be able to put together the different masses that a star could be. We found out that if we have a yellow star, which is going to be roughly the size like our sun, if it's with another one, then we notice that we have two relatively equal orbital paths of these two stars interacting with each other. However, if we have a system where we have one star that's going to be more massive than the other one, then we'll notice that their orbital paths are going to be a little bit different as such. We'll notice the one with the bigger mass is going to be a lot smaller. The one with the smaller mass will have a much larger orbital area. So this gave us a clue so we could start figuring out relative masses of stars. So the earliest way that we could find how far the stars were was by using this idea of parallax. And what parallax is it's an apparent shift of the background. So real quickly, if what we do, have you sit there, what I want you to do is hold your arm out in front of you and lift up your thumb like you're giving somebody a thumbs up. Close one eye and place your thumb over an object that's in the distance, and then switch eyes. And when you switch eyes, like close the other eye and open the eye that was shut, you'll see an apparent shift of the object. So it'll look like it's moved. You could measure that distance, and that would give you an idea of this angle. Okay, so through a lot of math, you can find this parallax angle that we see right here. Then if I extend this line straight from the star to the sun, and then come over to where the Earth is here, what it does is it gives us a right triangle, and then we can calculate what the distance is from us or from the sun to that star. Now this only works because we have this huge change in position. Your eyes only work a little bit. They're close together. But if you look here, if we took a picture of a star in the summer and then took it 6 months later in the winter, then what we'd notice is we have this big area, and we know this distance here. So because we know this distance, we can calculate this one as long as we know this angle. Now the idea of parallax isn't new. The ancient Greeks tried to do this to prove that the sun was in the center of the solar system, but unfortunately the equipment they had, they didn't have telescopes, so they weren't able to take accurate enough measurements to use this. Parallax is really good for measuring close stars, but it doesn't work too well with further away stars. Okay, so let's talk about brightness of a star. We call the brightness of a star its magnitude. And magnitude is kind of interesting. If we have a positive number, that's going to mean that it is going to be dimmer than those that have a negative number, which are going to be brighter. So the more negative the number is, or the smaller and more negative it becomes, the brighter that star is going to be. So we have that one, we can look at it that way, and that's how we rate our stars. So if you go back to Hipparchus did his star catalog, and he cataloged probably about 500 stars that he could see, and we still kind of use the same type of method that he did, because looking at brightness hasn't changed a whole lot for most of our stars. Now when we talk about magnitude, we have two different kinds of magnitude. We have what we call apparent magnitude, and then we have what we call absolute magnitude. Apparent magnitude is how bright is it from Earth. When we look at it, what's its apparent brightness? And we'll notice that if we take the brightest object in the sky and the brightest star that we see, the sun, it has an apparent magnitude of negative 26.7. So that's going to be really super bright. The closest star has an apparent magnitude of 0, and one of our brightest stars is going to be Sirius. Okay, and Sirius has a magnitude of negative 1.4. So these are apparent. This is when we're looking at the stars, how bright do they seem from Earth. Then we have absolute magnitude. And absolute magnitude would be as if we took all the stars and we put them at the same distance away, how bright would they be in relative to each other? And this is where we start to see some interesting things. The sun, that was a minus 26 and apparent, its absolute is a 5. So it's going to be kind of a dim star. It's only an average star that's out there. Alpha Centauri is going to be a 4. Sirius is going to be a 1.5. But take a look at some of these others. When you go out and looked at Orion and saw Betelgeuse, notice it was only a 0.8. So it was not a super bright star, but it wasn't very dim either. It's just kind of there in the middle. But notice when we have its absolute magnitude, it's going to be a lot brighter. And if we take one like Deneb, who is so far away that its apparent magnitude is a 1.3, its absolute is in 6.9. So we know it's a much bigger, brighter star, but because it's so far away, it appears to be a dimmer star. So even though you can look in the night sky and see two stars that look to be about the same brightness, because their distance from Earth is going to vary, B is going to look a lot brighter because it's closer. A is going to look not quite so bright because it's so much further away. So when we talk about magnitude of stars, apparent is what we see, absolute is if we put them at a distance. And it's important that we know the difference between those two types of magnitude. Okay, in this picture we have probably the most important diagram when it comes to stars, and that's the Hertzsprung-Russell diagram here. And we're going to talk about it, but I'm actually going to use a different one than the one we have in the lessons. So let's go to that one and I'll explain our way around the Hertzsprung-Russell diagram. Okay, so here we have a different picture of the Hertzsprung-Russell diagram, and there's a couple things I want you to see. First of all, what we're going to have is our surface temperature of the stars down here. And what you'll notice that makes this one a little bit unique is we have 3,000 kelvins here, but we're going to have 30,000 kelvins here. So it actually gets hotter the closer we get this way, and it's going to cool off a little bit as we travel down this way. Now, we can name our stars or classify our stars by temperature, and you can see this M through O classification. M are going to be the cooler ones, and then we'll go to K, G, F, A, B, and then O here, which are going to be our brighter stars. Now, on the other axis, we generally omit luminosity. How bright is it? And we measure that in solar units. So if we find our one luminosity, that's going to be 1 sol, and we'll notice it right here is where our sun is. So our sun is a yellow star. It's a G class. It's going to be about 5,500 kelvins warm, and it's going to have a luminosity of 1, which would make sense if we're measuring it against the sun. Now we can see there's different regions. We also have sizes. You can see here we have 0.1 solar radius. Here we have 1 solar radius. So you can see that a star on this line here, so if we go down here and we look at Proxima Centauri, which is right here, we'll see that that star is going to be about the 10th of the size of our sun. If we go up a little bit more, we have our 10 solar masses here. Here we have our 100 solar masses, and we even have 1,000 solar masses. So if we look at Betelgeuse, Betelgeuse is going to be about 1,000 times the size of our sun, just in the radius part there. So we can see that stars are going to get a lot bigger. Now, we have our small little red stars that are going to be over here, and these ones have been burning for a while, and we'll talk about that in the next video. We have what we call our main sequence, and these are stars that are doing what they should be doing at this point in time, converting hydrogen into helium for the most part. We have different groups on here. We're going to have our giant stars here, which we could see in Aldebaran and Arcturus. We'll have our supergiants, and this is where we get Deneb and Betelgeuse. And then, like I said, we have our main sequence, which is going to run up through the middle part here. And then down here, we have our little dwarf stars. Okay, and these are going to be a lot smaller stars. Okay, in fact, they're going to be 100th the size of our sun. So the HR diagram can give us an idea. When we plot these, we can figure out by looking at the color of the star, we can figure out how hot or how cool the star is burning. We can know by distance about how big they are. So it gives us a lot of detailed information on stars. Now there are a couple other things I want to show you some pictures of that we have out there. The first are going to be Cepheid variable stars, and Cepheid variable stars are stars that are going to vary in brightness. So if we look at this star here, okay, it's the Cepheid variable in galaxy M100, notice that it's going to go from being really bright to getting kind of dim, and then it's going to brighten up again. So what's going to happen is this star is going to kind of pulse in its brightness. It's going to go bright and dim over the period of a couple days. So these are variable stars. They help us figure out distances for the stars that are going to be a little bit further away. Some of the other things we want to talk about a little bit more in the lessons are here we have a supernova, okay? And this is when a star explodes, and we'll talk about that in our next video. And also we can look out and we can see some things like nebula here, and this is the Horsehead Nebula, and you can see why it gets its name. Okay, that's it for our video. Sorry this one was a little bit long. Good luck on your quiz, and we'll see you in the next video.